One problem with density functions is that a same random variable may have multiple density functions. Say I have this density function. It is always non-negative, and if you integrate, the total area under the curve will be equal to 1. So that is the density function for some random variable, say x. Okay, now if I just take this point and take it up there, which means I make this rounded and make the dot come here, which amounts to putting the equality case here. So now that is a different function, but this also corresponds to the same random variable. Because since I have changed it only at one point, the integral does not change. The only condition I need to link up this f with the x is that probability of x lying in an interval should be the integral of f over that interval. Now if I change the value at only one point, obviously the integral is not going to change, though this function has changed. Thus, both the original f and this modified f are actually probability density functions for the same random variable. And similarly, if I just pick any point and take this point somewhere here, that will also give me the same random variable or the same distribution, though the density function has changed. In this way, you can actually change the density at countably many points, and still it will be the density, it will be our density for the same distribution. This non-uniqueness of density is a little bit of a problem, but fortunately there is a theorem which gives a little remedy to this situation. The theorem starts with a random variable and two densities for the same random variable. Now we shall take a point A in R. And we want to have some condition under which we can say FA equals GA. But we know in general that is not true, because even if I change one of them at that single point A, it will still remain the density. So I need some condition. And the condition is that F and G must be both continuous at that point A. Then it is unique. Let us understand the main idea behind the proof using this picture. So here I have F, it is continuous at this point A. I have drawn it continuous everywhere, but what we care about is continuity here. Now I have another density which is also continuous there. Let, if possible, FA and GA be different. Then the graph of G would look like something like this. So the value GA is different from the value FA. It could be under it. I have drawn it above it. Now observe this interesting thing. What I will do is, since it is continuous and this is also continuous, it cannot be, G cannot be above F exactly at a single point. It has to be above F over a neighborhood of A. Here I can see that this is a neighborhood of A where it is above. So consider this neighborhood. I will give it a name. Suppose I call it N. So that is the neighborhood. Now what can I say about probability of X belonging to N? Since F and G are both densities, I must have this equal to, so it is integral over N fx dx. So if this N is from alpha to beta, you understand that I am writing alpha here and beta here. And also, since G is also a density, I must have integral of gx dx is also same, but that cannot be, because I have chosen the neighborhood in such a way such that G is always strictly above F. So clearly there is this area cannot be 0. So if I subtract one from the other, I cannot have 0, because it is not positive somewhere and negative somewhere that they can cancel. It is always positive. and that will give us a contradiction. Now that is the main idea of the proof. The exercises will explore the detailed steps. So here is the problem. Let fg be any function from R to R such that whatever 2 points alpha and beta you take, their integrals, Riemann integrals, always match. So in particular, their Riemann integrals are always defined. They are Riemann integrable. Now, at some point A, f and g are both continuous. Then you have to show that f of A must equal g of A. So I shall give you the outline of the solution, and the problem that you have to solve is to fill in the details. The proof will proceed by contradiction, so let if possible they be unequal, which means without loss of generality, say fa is smaller than ga. I consider hx equals gx minus fx, which must also be continuous at the point A. Now you have to give me an epsilon, strictly positive, such that there will be a delta such that whenever you take x in a delta neighborhood of A, hx will be strictly greater than epsilon. So looking at these two lines, you have to choose a suitable value of epsilon. You have to actually give me, in terms of A, G, A, etc. You have to give me an epsilon such that this will happen. Once you get this, now you have to argue that this thing cannot be equal to 0. This will immediately contradict our given assumption. So your job is to complete this proof in a completely rigorous way.